where we are in the course. Like I mentioned, so we have part one is focusing on diffusion of heat and mass. So we have discovered flux relationships, conservation equations, and boundary conditions. We have now done this several times. And then last couple of lectures, we have been starting going towards 1D study problems. So the first problem we discussed was the first order reaction in a tube study problem. We got the concentration profile for A. The second problem, which is what you also did in your homework, the gas diffusion problem of A going to 2B with a surface reaction. And so we learned how gas diffusion, you have to be careful with conservation equation. And last class, we discussed the approximately 1D study problem, where we are going from 2D to 1D. Just to remind you, so the main idea behind this problem was that when HW by K is less than 1, we can use boundary condition, ignore the variations in Y. So that really meant that temperature in X and Y can be approximated. That's an average temperature in X. Okay, so that was the main assumption that allowed us to kind of get and make a 1D problem out of it. Okay, so the second problem we started, which we did not finish, which is what I want to do now, is we discuss the 1D unsteady problem and how we can make it 1D steady. So the problem was an organic liquid in a vertical column. So think of it like acetone in a liquid column. A being the air. So let's just remind, A means the air and B is the organic vapor. We are saying outside the tube, the organic vapor concentration is 0 and air concentration is C, small c. And this organic vapor is evaporating with time. So this height h of t, which is the vapor column, is increasing with time. So y being the direction downwards in this case, and Cl is the concentration of pure B. Okay, so it's just pure B. That's the concentration. And by using partition coefficient, one can find that the concentration at the interface for Cb is Cb naught. Because the problem is isobaric and isothermal, by ideal gas law, we know P is equal to CRT. So C is equal to Ca plus Cb is equal to always constant. So that also gave us that at interface, Ca is equal to C minus Cb naught. Okay, so that was another thing we learned from the problem. Okay, so this is what we did. Then we started with the governing equations, and I'm not going to kind of discuss in detail, but I'll just quickly write them down so that you can remember what we discussed last time. So the governing equations, and recall we mentioned that this is only in gas phase. So we are writing the governing equation in gas phase. Liquid phase is separate, and because liquid phase is simply this concentration being Cl of the B phase, so it's not interesting. So in the gas phase, we say NaY is equal to constant. I mean, so the equation was really dNaY by dy is equal to 0 and dNby by dy is equal to 0, which implied that NaY is equal to constant, NBY is equal to constant, and the boundary conditions were Ca at y equal to 0 was C, Cb at y equal to 0 was 0, A at y equal to h of t is C minus Cb naught, and Cb of y equal to h of t is equal to Cb naught. Okay. All right. Before I forget to mention this again, so remember that we are ignoring any of the time dependence here. So we are ignoring time dependence here. Let me just write it. Del Ca by del t, because it's a pseudo steady assumption. And basically what that means is, and same for Cb, just remember that. We're ignoring this because we are saying that evaporation is much slower than diffusion. Okay, so diffusion is instant. Another way to think about this is that diffusion is so fast that there is no time dependence. And we will discuss this in a lot more detail. Okay? So that's why we ignored it. And so some of you may be wondering, how come I have h of p here? So I didn't write it like this last time. So height is a function of time, and I'm writing a boundary condition as a function of time. Why is that allowed? Any thoughts? Anybody wants to say why can I write why? Like why can I use a time dependent boundary in this problem? Absolutely right. So does everybody follow what I said? Is basically at y equal to h of t. H of t doesn't matter here because h of t changes so slowly. Evaporation is so slow. At each instant, it is basically a diffusion. It's just like instantaneous. So this is constant for the diffusion problem, it may be changing globally, but when I'm solving diffusion, it is constant because diffusion is so fast that height can be assumed to be constant, even if it is a function of time, because diffusion is so fast. Okay, and we'll discuss this in more detail today. All right, we did this and we said, well, to make more progress, clearly we don't have enough information. NAY and NBY, we don't know the value. So then we applied the interfacial balance, which is obviously because there's an interface and it's evaporating. So we applied the interfacial balance. This is the last thing we did in the last lecture. And I will just give you the results, which we did last time. So the results was NA was, NA was C minus CB naught into velocity of the interface VI. NBY was minus CL minus CB naught VI. Okay. So this was the flux we calculate for A and B. And let me sketch it again here, just so that we can discuss this once more. A comma B. And this is Y equal to H of T. This is Y equal to 0. C is equal to C. CB is equal to 0. CB is equal to CB naught. And C is equal to C minus CB naught. Okay. So the reason I want to emphasize this here is that the interface with time, what do you think it is going up or down? Down, right? It's evaporating, so it's going down. So in Y, basically in terms of Y, it is going down. The velocity is actually positive because note that my Y is in this direction, right? So interface is going down. So my VI term is greater than 0. And what do you think? C minus CB naught, is it positive or negative? C minus CB naught. Positive, right? Because the total concentration is C and CB naught is only a part of that concentration, right? So because remember that CA plus CB is always equal to C. So small c is greater than CB naught. So what it is saying is NAY is positive. Okay, so that we know that NAY is positive. And does it make sense? It's saying that flux of A is in the positive direction. And remember that Y is pointing downwards. And how can you understand that? Note that the flux at the top of the column is C for concentration of A, and whereas concentration of A is C and concentration of A down at the interface is C minus CB naught. So it's lower, right? So it's going from higher concentration to lower concentration. So it's going to go in this direction, which is positive Y. That's why NAY is positive. Now let's look at NBY. NBY, again, BI is greater than 0, and concentration of the liquid phase is always going to be greater than the gas phase because concentration is related to density, and density is 1,000 times more for the liquid phase. So the NBY is negative, and that means because my concentration of B at the interface is CB naught, whereas CB is 0 at the top, B is going on the opposite direction. Okay, so note that NA is going here, and NBY is like this. Okay, and NBY is on going top, so that's why it's opposite to Y. That's why it's negative. Okay? Does it make sense to everyone? Any questions on this sign? Okay, so just when you're visualizing this, remember that it's a binary gas diffusion problem. Air is coming in and vapor is going out. Okay, so we have this now. Let's say, how do we proceed further? So we have these equations now. NAY is constant, NBY is constant. We know the value of that NAY and NBY in terms of VI, and we have the boundary condition. So what is the next step? Anybody wants to suggest? How do I proceed further? Sorry, yeah, go ahead. Great. So the great suggestion. So the suggestion is determine the velocity, which basically implies that we want to write the relationship for NBY and NAY. Okay, so what is NBY and NAY? So by the way, I will be just for simplicity, I'm focusing on NBY because it's the organic paper. And remember that you can always use this CA plus CB is equal to C to get the CB. Okay, you don't have to solve for both of them. You can solve for one of them. So NBY, so I have two options. One is this one. Let me just do it with Y because it's a 1D problem. D omega A by dy. Or I have the option of, or I have the option of this one. Any thoughts on which option should I choose? We have discussed this before, but which option do you think you should choose? Is it the mass average or the molar average? Molar average, right? Because here C is constant. If rho is constant, you go with the mass average. If C is constant, you go with the molar average. And if you do not trust me, you can always try to go with the other option and you will see it will be 5 times more difficult in this problem. Okay. So whenever you see C as constant, just remember molar average velocity. Okay. And it's easy to see why, because chi A is Ca by C and d chi A by dy thus becomes, because C is constant, it becomes 1 by C dCA by dy. Or basically I will choose this option, which means Cb V molar minus DAB dCA by dy. Okay, so this is what I get. So this is essentially the problem I will choose, and I have and note that I already know what NBY is. It is minus CL minus CB naught VI. Okay. So can I stop? Yeah, so. Oh, sorry, my mistake. Thanks. Sorry, C. It's always chi B here. My mistake. Thanks for. This should be. I'm just out of habit writing A instead of B. This should all be B. Thanks. Okay. You're right. This should be all B everywhere. Even here, it should be d omega B by. Sorry, yeah. So this I just have it. It's just common to use A as a variable. Okay, everything hopefully should be fixed now. Let's check it. Right. Yeah. Sure. Yeah. Correct. So DAB is always equal to DBA. So remember that we had discussed this briefly. DAB is always equal to DBA, and that is because, as we had briefly discussed in almost I think first lecture or the second one, where we said omega A plus omega B is equal to 1, and that forces DAB is equal to DBA. Okay. So this is always going to be true. So you can always use DAB. All right. So can I just solve it? Yeah, go ahead. No? Oh, so that's a much more complicated problem. So for a multi-component diffusion, we will not go into that in the class. But like just sort of kind of explain, diffusion becomes a lot more complicated when you have like multi-component. So the book actually has a chapter, but we don't cover in the course. It's given. If somebody is interested, and then there is like a chapter in the book. So can I just solve it now? What is missing? Can I just integrate this problem right now? What is missing? Vm, yeah. So we don't know Vm. Great. So we don't know V molar. So let's just find V molar first. So V molar, we know is NAY plus NBY by CA plus CB, or NAY plus NBY by C. Okay. That's the definition of V molar. That's the sum of VA NAY plus NBY by C. And NAY and NBY, I've already calculated the expressions in terms of VI. So you can substitute the expression. So remember, this was C minus CB naught VI. And this was minus CL minus CB naught VI. And if you do that, then essentially what you will get is, you can substitute this, you will find it to be CL minus C VI by C. Okay, so this is what you will get as the molar velocity, CL minus C by VI by C. Make sense? Any questions here? All right, so what do you think? Is V molar constant or is it V molar changing? Constant. So why do you say so? Yeah, it is constant. So CL is constant, right? And C is constant. But what about VI? Is VI constant? The interface velocity, do you think it will be constant? It's moving down. So we don't know if it's constant, but what do you think? Should I assume it to be constant, or do you think it's changing? It is changing. So then how can I proceed then? So what do you think is the catch? It's changing very slowly because it's changing by the rate at which evaporation happens. We are solving a diffusion problem. So everybody is right, it's actually changing, but it's approximately constant because diffusion is so fast that at that particular instant I can assume. So essentially the diffusion problem, when we are doing the diffusion problem, all of these time dependent variables can be assumed to be sort of a value because you're solving the diffusion problem. And then when you relax, once you have solved the diffusion problem, you can solve it at the problem of the evaporation. And that's where it becomes a function. Okay, so we'll discuss this in more detail, but I just want to clarify that this VI function here is the velocity of the interface. And it can be a function of time, but it can be a function of time when I'm really thinking about time of evaporation. When I'm thinking of diffusion, diffusion is so fast that this is much slower. Changing. So generally, I would say, so the question Noah is asking is it possible that evaporation is actually faster than diffusion? I would say generally, whenever there is a phase change, and we will discuss this in a bit, but whenever there is a phase change is generally slower than diffusion. That's as a rule of thumb. But what if the velocity of the interface is not because of a phase change? Right? In that case, you may not be able to use pseudo-state dimension. So whenever there is a phase change, generally I would say phase change is a slower problem and generally speaking. So in most cases it is okay when it's a phase change, but when there may not be a phase change, there may be like let's say a liquid interface, right? And it's just kind of moving. And in that case, you may not be able to do that. Any other questions? All right, so we have established Vm is constant. So before, just a small question here, just out of completeness. What do you think would velocity of the mass average velocity be in the gas phase? Would that be zero, non-zero? Let's take a quick poll for that. What do you think? Will it be zero in the gas phase, or do you think it'll be non-zero in the gas phase? Let's do a quick poll here. Hopefully you can see, and we'll just keep it quick because it's just a yes and no answer. Let's hopefully it comes through. Yes, should be on everyone's screen. So select the response, yes or no, and then we'll talk about it. All right, I'll give another 30 seconds, quick question. So let's wait for another 20 seconds and then I'll close out the poll. All right, last 5 seconds or so. Please participate. All right, I'll close now. All right, let's take a look at results. It's split, a little bit split. So why don't you talk to your neighbors, see if you got the same answers or different answers and convince each other. All right, so let's discuss this. So the answer is no. It is actually non-zero. And you have the formula, right? You have the mass average fluxes should be combined, and then you can add NAY percentage NAY and rho. And as you have the expressions of NA by N and B by. Note, this is different from the reaction problem that you did. In the reaction problem, you couldn't have unit mass. You give something visible. So the phase in the gas phase, you're adding the mass of B. So it does come up with a non-zero. And the supplementary video I talked about does actually derive this value. and derive value in another derivation and show you how the two values are the same. So basically, it does another intersection balance in continuity equation. Again, this will not be required for you to do. Just out of curiosity, if you want to see, you can calculate this velocity from two different methods, and you can get it to be the same value. So I encourage you to look at the videos. You can see kind of clarify this one. But you can see that this is actually, if you just sum the values, it's not going to be necessarily zero. So now another question: do you think it's constant or it's changing or is velocity in the gas? Mass average. You know the molar average velocity is constant. So is the mass average velocity is constant? Any thoughts? So I got some. If you have a question. So I heard one. Someone said no because density is changing. Anyone else secondly or has thoughts? So what about the numerator? Is numerator constant? NAY is constant. We just discussed it. NBY is constant. But what about density? How do I know what density would be? So the way to think about density is, remember that density is CAMA plus CBMB, and this is equal to C minus CBMA plus CBMB. Because C is constant, as you can see, unless my MA and MB are the same, which is what we did in your also in your homework problem, you can see the CB will remain, right? The mass, unless the MA is equal to MB, you will not get a constant number because CB is changing. CB is changing, you know that. So rho will also change, unless the mass of the A and B are the same. Okay? So your velocity is actually not constant space. Sure. Yeah, V is non-zero.
Right. But I know that you said, like, if we don't take into account
So the evaporation, we do take into account the boundary condition. But all we're seeing is the rate of change of evaporation is happening at the longer time scale. So I mean, if we don't change, if we don't account for any mass change, then there is basically not in a solution, right? So all we are saying is that there are two time scales in the problem. Evaporation just happens very slowly. So I'm just considering one height, it's evaporating, it's giving some input to the gas phase, but that's it. We're not worried about how fast it's going down at that extent. So it's so far. Any other questions here? All right, so V in the gas phase is this. So now let's think about V in the liquid phase. So what do you think will happen in the V in the liquid phase? Is it zero or is this not zero? Let's do like another minute or so. Yes. Right. It's a total mass flux divided by volume. That's a great question. Yeah, I will answer. That's a great question. I will answer this. So let's maybe another 5 seconds. Let's quickly get here. All right, so let's look at the results. So it's again split. So I will let you talk to each other and let's see if we can change each other's mind. Okay, so talk to each other and let's discuss this again. What do you think happens at the liquid phase? All right, so the correct answer is yes, it is 0. And I just have it here. Right, it's here. So it is 0. And just to kind of give an example, and again, I go a little bit in more detail, supplementary video for this, is that you can think of it because it's a single component, right? So continuity equation happens for the entire system, right? But in the liquid phase, there is only one component, that is the entire system, right? So it's easier to calculate the velocity there. Rho L is constant, right? And density is constant, it's a pure B. So the velocity has to be constant. And the velocity is 0. They cannot have velocity solid phase. So velocity is 0 everywhere. Okay. And that is also the reason we said flux is 0. Because when the velocity is 0, in this case, there's only one component. So mass average, molar average are all the same. So there is only one component. It's a pure B. It's pure B. So pure B, there cannot be any change in density, right? So the velocity is 0. And so basically, you can convince yourself that it's constant and 0. Okay? In the case of the gas phase, molar average velocity is constant and non-zero. Mass average velocity is non-zero but not constant. Okay? So there are all these sort of certainties there. And then I try to go into this. Okay? So Noah had an excellent question. Noah was saying, well, you said that we are adding mass, which is a great question actually. So maybe my explanation was too simplistic. You said, well, you're adding mass, you are saying that fluxes have some sort of gas fluxes in the positive y direction, right? And then there's some flux in the negative, and there is also flux in A in the opposite direction. So why are you saying that the velocity is sort of, why can't these fluxes cancel each other, right? That was the question. It's a great question. So if you think about this, how can I convince myself that the fluxes won't cancel each other out? So does anybody want to look at this formula on top and give a guess of why do you think the fluxes can't cancel each other in this case? Either mass or molar average. Different molecular weights. So Sophie suggests that well, there are different molecular weights. So that's a good observation. But if I say M is equal to MD, then you can see, well, I'll get some density, right? Then the mass average velocity, I'll still get some sort of a value which is not necessarily going to be 0. So I can still substitute M is equal to MD and get a non-zero answer, right? So it doesn't necessarily imply that I need to have difference in molecular weights. Difference in molecular weights might just make my density constant. That's all. That doesn't cancel out the fluxes. Great. So that's where we are going. Is that look at the reason why we see this value to be non-zero is this term here, Cl minus C. It's saying there's a difference in the molar density or concentration or mass density you would like that is more physical. If there is a difference between molar and the molar density, then I get a molar velocity, right? And that's absolutely critical. If there is this density difference causes this change in balance, right? So the point being that you are evaporating a liquid, right? So the flux generated because of that is much higher than whatever the flux will be coming in. You can see that. So what I'm trying to say is Cl is greater than C. That's, you can expect that because that's by definition density of any liquid is much higher than the density of a gas, right? So let's look at NaY and NBY. So what Noah was saying is, well, they're opposite in each direction, but can't they cancel each other out? But let's look at NaY. NaY is C minus Cv naught. So that's kind of like a gas phase molar density multiplied by velocity. Whereas for an NBY, I have a molar density multiplied with the velocity. The flux of the B is much higher than flux of the B, right? Because the density is much higher in liquid. So that's or motor density is much higher. So these arrows are deceptive in that sense. The reality should be, and it's an excellent question. This is the reality. NAY may be positive, but it's much smaller than NB1 because densities of the liquid field are much higher than zero. So that won't be the case. You wouldn't be able to solve. Correct, absolutely. If it was not the case, as you will see, I will just see in 5 minutes, this will not even be a zero system. If this was just a gas phase leaking some from another gas to another phase, that you will not be able to say evaporation. The evaporation is critical here. It's a liquid going into a gas, and that liquid phase having such a large density makes all the difference. If it's like a let's imagine there's some sort of like a membrane, okay, membrane which is sort of feeding some flux, and these are two gas phases. All of this analysis fits because a gas going into a gas, my NAY and BY will be similar, and you will see you'll not even be able to assume some sort of like solution. It's very critical to understand that these fluxes they're opposite, but they're very different in mass. Kind of like this. See that, and it's a great questions again. I would not have thought about this had this question not been asked, right? So great question. NBY is much greater than NAY, as you can see, and that also physically makes sense, right? That if something is evaporating, that will have the predominant flux. Why should air have such a large flux? Because there is no much greater reason for air to kind of going inwards. It goes a little bit, but it's not going to matter as much as compared to something that's evaporating. So that's why it's has a larger flux. Okay. All right. So let's keep going. And again, check out the supplementary videos if this is a little confusing. Hopefully that will help further with this philosophy. Yes, questions. I have to think about it. It's possible, but I have to think a little bit more. I would say yes, because since we have started in the paper, we do a problem in the homework. We do have an osmolarity problem. Osmolarity. We do have it in the homework here. So we don't have it. We don't have it now. We used to have it some years. So basically, whenever there is a phase change, generally that is true. And sublimation is also a phase change. So I would presume it's true. And there it extends into a solid. It's probably even more true. But I have to think about it in case maybe it's not. But I don't imagine. Probably it's also true. Any other questions here? Yes, please. Correct, in the B phase. So you can also apply that. Great question. So let me just answer the question. You can also apply this in the gas phase. Then it will be d by dy of rho v is equal to 0, right? Because rho v is constant. Great question. So that's a great observation. So the question is, well, v is not constant, rho is not constant. So like how can we get? So that's fine because we are saying rho v is constant. So both can change, but they'll change inversely. Yeah, proportionally to that technology. Great question. So this has to still hold. I don't do this full problem because solving for full density is very difficult in this problem. But you can try if you want, and you will find this it has to hold. Right. Any other questions? Great discussion. So let's keep going. So now we have the value for Vm. We can now substitute Vm here and then solve the problem. So I'll do that now. So substitute Vm into the equation, into the governing equation. Okay. And what you will get is this. So you will get minus Cl minus Cb naught Vi. This was the flux of the B and By term. Then you will get minus Cb into Cl minus C Vi by C. This is your molar average velocity term. And then finally, we have minus DAB dCb by dy. Okay, this is what we get. Just a quick note here. It is possible to solve this problem more exactly, but for simplicity, because we were just discussing this, we know this liquid density is much greater than gas phase density, right? So we are just discussing this. So I will approximate this as minus CB CL by C VI. Okay, just out of simplicity. And what can I do about this term here? Any thoughts about this term? CL minus CB naught? No, still CB naught, right? Because again, CB naught is a smaller than C. CB naught is even smaller than small c because it's just a part of the concentration. So I can also say this is CL VI minus DAB dCB by dy. And this is, again, you can solve it. It's not required. I'm just making this because it makes a little bit easier to see the whole results. And I will just rearrange and give you the final result, dCB by dy, just to make sure I don't make a mistake. 1 minus CB by C is equal to VI CL by DAB. Okay, so this is what you get. And we can integrate VICL by DAB dy. Remember, we can integrate from 0 to h of t. And the concentration at y equal to 0 is CB is equal to 0 to CB naught. This is not very clearly written. CL here. CL. Integration of 1 by 1 minus x is log x term. So if you will do this, you will get finally, I'll just give you the result. It's not, it's, takes a little bit of time, but it's possible to do this. VI is equal to minus DAB C by H CL log of 1 minus CB naught by C. Okay. This is what we get. This is the final result we get for the I, and we get this expression. So great. So this is the problem. It does not just starts to tell you how the velocity of the nucleus is changing, right? And I hope you can all see that now I can say this is dH by dt, right? So it's changing with height, and dH by dt is this. And I can integrate this further to get the answer. One approximation you can make, and this is by no means necessary, this is just to simplify and show you something interesting, is I will write this as, I'll further say CB naught by C. This is again not required. I'm just doing this out of simplicity. CB naught by C is much more than 1. And I hope you can remember that 1 minus log of 1 minus x much more than 1 is minus x, right? Log of 1 minus x for x much more than 1 is minus x. So that allows you to write dH by dt as DAB C B naught by H into 1 by CL. Okay. All right. So this is what you get. As you can see, if I integrate this now, I will get some sort of an x squared term on the left side, t term on the right side. So you get an x squared versus time of that. The height decreases. So height increases as the square root of time. This is the problem. One thing that we have not discussed yet is a pseudo-steady assumption, and that's what I want to go further now. So I've been saying again and again, velocity is changing much slowly, and evaporation is much slower. How can I prove it? How can I prove that velocity is much smaller than the diffusion time scale? Is anybody any thoughts on how can I estimate evaporation time from this formula? That's it. What would be a way to get like time from this form? We have a velocity, right? Velocity. The left hand side is velocity, right? So time is distance by velocity, right? So that kind of get a rough estimate of time. So T evaporation in that way, you can approximate as H by dH by dt, right? That's not a bad idea. You can just say H by dH by dt. And if you do that, what you will find is it will come out to be H square by DAB CL by C naught, CB naught. Okay. So this is height by speed, right? Just to get a sense of, because that's a change of, it's a height by how fast the velocity is changing. You get this as a formula. You can, I believe that is what we should get. You mean the h square by dt or the okay, this is h by dh by dt. This is T evaporation. T evaporation. So this is evaporation rate or time for evaporation. Time for evaporation. Let's see. And then I'm saying this is H over dH by dt. What is this?
So it's where the height of the interface of the chain.
It is the height. It is the height of the vapor column, right? H is defined as the height of the vapor column
Oh,
of the gas phase, right? That's how we define the height. This is the height here. Right? So it is just that. So we are saying we know the value of dH by dt here. So I have just substituted this here and just got something in terms of H by dA.
maybe start
Oh, that's true. So that we are not solving. Yeah. So that's a good question. So how H is also a function of time. So you're asking what H should I choose, right? It will be zero initially and it'll keep on going and will go until the length of the tube. So you can think of H as the length of the full column. That's like if you want to find the overall time to kind of evaporate roughly, the H will be just the length of the column. But it's kind of a scale. This is not a value. It's kind of an estimate of the time of evaporation. Okay. And time of diffusion, and I believe this is something we'll discuss several times in the class. Time of diffusion is actually given simply by h square by dAB. And we'll discuss this more. It doesn't depend on the ratio of concentration. It comes out to be h square by dAB. So what does this mean? You can just tell you something. It tells you that time of evaporation is much higher because there is a ratio of liquid density to the vapor density. So it's much lower. If again the phase change, the requirement of the phase change makes the evaporation much lower, whereas diffusion doesn't care about the phase change, simply the distance squared by the. That's why you can assume that evaporation is much much slower than diffusion because the time for evaporation is much larger. Okay, and that justifies our pseudo steady assumption, and that's why we are able to reduce from a 1D unsteady problem to a 1D steady problem. Any questions here? Yes, please. Sure, sure. Yeah. Yeah, so absolutely. So this is basically what I'm doing is I'm using so log of 1 plus x is x minus x squared by 2 plus x cubed by 3 and stuff like that. That's like it's like you when you do a Taylor series expansion for small x, that's what you get. And for small x, you can ignore these terms, and then that's how you just say x. Yes, please. Absolutely, absolutely. If the liquid somehow, I mean, it's not possible because it's a liquid. But if I was able to, if I had a hypothetical liquid, somehow I had the density same as that of a gas phase, I can no longer do all of this assumption. That's not possible. But if I had a fictitious liquid that somehow had a density to be similar, then I won't do it. Absolutely for evaporation, I will listen to you.
So you said evaporation is
Larger.
much
Because CL by CL not. Yeah, sorry. Maybe I might have misspoken too, but CL is much greater than CV naught, right? So this number is much greater than 1. Faster. Diffusion is happening much faster. Evaporation time is longer, so it's slower. Yeah. Yes. Oh, yeah, that's the first question. Yeah, so let's discuss this a little bit more detail. It's a typical scheme in thing, but just to kind of, so Noah is asking, how did I even come up with this diffusion? So the idea is if you have something like this, so you have a derivative that is square. So we'll discuss this more detail. But essentially, you can see that there is an x square, that is equal to that and reflection. We'll discuss this after. Any other questions here? So let's take a break. Right now it's 12:52. Let's take a 4 minute. Let's come back at 12:56. We'll start and then we'll go towards 1D unsteady problems. Okay, we'll come back. Let's do that. And then. Oh, in the recording. Yeah. So yeah, it's being a little bit difficult, but I'll figure out a way because what's happening is because I go around the microphone is not moving as well. So let me try to kind of figure out a way.
Okay, yes.
Oh, there are no
Oh, you
notes.
do?
I probably do. Yeah, I should have all the notes,
Yeah.
but yeah. Oh, I see. Yeah. So if there is a persistent issue, don't hesitate to mention. There is a way to connect it with the microphone here, but it's just much more difficult. So that's why this program is more easy. But let me know if anything is unclear for Friday.
So for the equation that you're trying to solve for concentration, or why does it matter if the I is constant or not?
So it's a good question. It's a time dependent
You're solving
value.
the problem why.
Right. So the question then is if it's VI is changing with time,
You can still solve it.
you can still solve it. It's consistent.
Yeah, it's just not consistent with the pseudo study process.
Sure. So that's what I wanted to emphasize. So you can still integrate in Y,
Yeah,
but it's a value which is changing.
yeah.
And
So it's not like the problem is here. The problem is actually in the formulation.
formulation. Yeah. The problem will be in the formulation.
Okay. Yeah. Cool. Oh, and so to answer the question that I did in the previous class, I guess the information about your phases is contained in the partition formulation. And that's what dictated in the time scale.
So we'll take like a snapshot of your guys'. Because you just so this rho visible constant is simply trying to say that micro momentum is right. So that's so what I think what you're trying to do is not just the product is constant, but the rho visible constant is the function that the momentum has to be constant. Yeah, so I wouldn't try to like.
I was trying to correlate if you have like some mass, let's say each particle figure its size must be right? And then some other mass. Yeah, scan, I guess what would do is but if you sum all those micros together, like very constant, like their mass,
So what I'm trying to say is like that's what we will say it's possible that you just have some pieces. Because you don't have the process from
so you asked about the interface velocity, so that the road is
All right, let's get started. We are now going towards chapter 4 indeed. We're going towards chapter 4 indeed. And that is first problem we will start is 1D unsteady problems. And by the end of next Wednesday, we would also be able to solve 2D unsteady problems. But we'll mostly focus on 1D unsteady and 2D steady. But you would have the toolkits to solve 2D unsteady problems with the reactions and so on. Okay. So now we are going. So first, fluxes, conservation equations, boundary conditions. Start with the simplest example, 1D steady problem. We then went to a little bit more complex, which is approximately 1D steady problems. So 2D steady to 1D steady, then 1D unsteady to 1D steady, okay, which is the similar steady problem, which we just did. Now we are going towards 1D unsteady problems. And the first problem we will think about is a liquid column, which has Ca is equal to Ca naught. So this is a pseudo binary system. We're just thinking about system Ca naught. This initial liquid is a liquid is free of Ca. This initially does not have A. So again, I like to think of it as carbon dioxide being pressured into water phase, so dissolving CO2. So initially water was free of CO2. Now you are kind of pressurizing on one side. This is X. This is infinity here. It's a very long tube. And for if we are saying that basically we have to solve the problem of Ca of X comma time now. Okay. So now note I have X comma time. This is what I want to solve. So this is the problem we'll start to how to solve this flux. Right. So just to again iterate, long tube, exposing one side of the tube to the gas A, which then dissolve and gives the concentration Ca naught. If again I had given you the pressure outside, I would need a partition coefficient or a Henry's gas constant to get the concentration inside. In this case, you already know the concentration inside of the liquid is, and I want to find Ca X comma. So first step again, governing equations. Governing equation in this case, we have, so I've been using d by dt. Now I'll start using partial derivatives because we have now x and two dependencies. Del C by del t plus v dot. By the way, I should mention here liquid is stationary. So liquid is not moving. There is no velocity. Liquid is stationary. V dot del Ca is equal to dA del square Ca plus Ra. This is my governing equation, right? So we say there is no convection because the liquid is stationary. If the liquid was moving, then I would actually take into account this. Then there is no reaction. This goes to 0. No reaction, no volumetric reaction or surface reaction. And I get del Ca by del T. It's a 1D problem. So just del square Ca by del X square. And I don't have to worry about the other terms. This is my governing equation. The exchange saying basically that the accumulation is equal to the change, basically balanced by the diffusion. So that's the balance. Any questions on governing equation? This is what you want to solve. That's not clear here. So we have just dropped the convection term.
So do we not have to worry about the whole mass average, mole average velocity?
So it's a good question. So what Colin is asking is why am I not worrying about the mass average, molar average velocity? We just did it. Even though things like they weren't moving, they will still have velocities. The difference is, remember, this is a pseudo binary system. So we only think about those kinds of velocities, mass average, molar average velocities, in terms of like trying to calculate them. If I have a gas phase system. If I have a liquid phase system, whatever is the velocity of the liquid phase will be the velocity of the entire system. Okay? So pseudo binary system, makes that way life easier, because whatever will be the liquid of the whatever will be the velocity of the solvent will be the velocity of it. That's why it's much easier. So here you don't have to worry about those velocities because liquid is right now stationary. So you don't have to worry about that. Oh, well, I have to calculate molar velocity, mass average velocity, because it's the velocity of the liquid. That's the most abundant part in the system. So that will determine my efficiency. Does this clarify, Colin? All right. So we get this problem. Next is boundary conditions. And now I will write initial conditions as well, because I have a time derivative. Boundary and initial conditions. Okay. Boundary initial, and then second step, given equations, boundary conditions and initial conditions. Now let's start with the initial. What is the initial condition? Liquid initially does not have A, right? So it's zero. So we cannot have any, because it's free of carbon dioxide or free of any species A. So CA of x comma 0 is 0. It is simple. We have been given the value at, so 0 comma t. We have been given this value boundary condition at the first interface. C, sorry, I think it's CA of x 0 comma t C naught, because that's the concentration I've been given, right, at the inlet. So this is CA of 0 comma t into C naught. And then finally, we have the second boundary. So what's the second boundary? Sorry, I shouldn't have written this. But the second boundary is the infinite, the second portion, which is far away into the tube. That's infinity comma t. Infinity comma t. And that is also 0, because when I'm dissolving something, it's never going to reach really infinity. Probably will be free or carbon dioxide. So this is my constant value, straightforward. In your homework problem, you solve a similar problem, but with a flux condition. That's the difference. And that changes the things a little bit, but its process is similar. Okay. And we'll post a supplementary video also to kind of help you with that. All right, so this is sort of the boundary and initial conditions. It's a 1D unsteady problem. So it's a partial differential equation with these conditions. So what do we do? What do we try to do? Hopefully you have seen this in math method as well. So when you have a PDE, you try to convert it into an ODE. Okay, because ODEs are easier to solve. And this was actually one of the most important contributions in sort of mathematical sciences in a way, like in 1900s. A lot of discovery that happened was by converting PDEs into ODEs. Okay, so there are very sophisticated methods. What we will discuss is a very simple methods for the semi-infinite system. That's the similarity transform. And we'll just discuss it briefly. And we'll also give you examples for that. Okay. So when you see semi-infinite system, so when you see semi-infinite, think of similarity transform. Okay, similarity transform. And this is somehow I have seen over the years, this sometimes students don't find this to be very intuitive, and they don't find this to be an easy method, but it's actually, if you think about this, it's actually not that complex. And I'll try to show you some examples in sort of, so there is a fluid mechanician who mentions that you can think of scaling down of physical objects. That's really just simply what similarity is. Or the famous example I would say is this is an explosion by G.I. Taylor, who is a famous fluid mechanician. And what G.I. Taylor did was actually showed the similarity transform to estimate the energy of the atomic bomb. And it was very accurate. Use similarity transform to get to the dimensionality, dimensionless variables, and similarity transform to get to that similar solution. Okay? And in fact, this method was recently used for another explosion. Again, you just use images. You see the cloud. You can see that there is sort of similarity, physical similarity in the clouds, sort of the bomb, and you can use that as a way to kind of estimate the energy. So this sort of method to kind of has a far-reaching impact on how you think about it. It's not always old stuff. This is a paper from 2020, so just 2 years back. This is a liquid draining, and this was another similarity transform solution. So again, you can see geometric similarities that come out in the system. So when do you think, when should we be using similarities? Is when you can see that there is some sort of a preservation of a shape. Okay, so here the shape is preserved, right? The shape is preserved here. So this was actually a two-dimensional similarity. Here shape is being scaled down. It's not identical, but it's being scaled down. Okay. So that is the idea of similarity transform. So I really want to emphasize that when you're thinking of similarity transform, think of something being scaled up or scaled down. All right. So let's see how this is related to this problem. Okay. So let's sketch concentration profile. Okay? So concentration profile with X for different times. So what's it at T equal to 0? It's 0, right? We just discussed the initial condition is 0. So it's something like this. But as soon as T equal to 0 plus, I know this concentration is Ca naught, right? T equal to 0 plus, I have made this sort of expose this first T equal to 0 with Ca naught, right? Then I have added, as you can imagine, I'll start to slowly kind of push this inside. And I'll start to see some sort of like a system which is sort of going further and further into the system. And what really we are seeing is if I sort of find some sort of a value which at which this is being spread out. So X goes from 0 to infinity, right? But I don't care about the entire region. If I'm initially here, then I don't care about this region beyond this point because the value is 0 everywhere. So I really care about the region where concentration gradients are present, right? I don't really care about the region everywhere because it's always infinite, right? I just care about the region where concentration gradients are present. And this region where concentration present is called boundary layer. So this is the region where concentration gradients are present. Concentration gradients are significant or sort of like not vanishingly small. Are significant. Okay. Yeah. Yes, delta of C. Delta. Yeah. Sorry. Delta of C. Okay. Delta of C. And what the whole idea of similarity is this. So again, I want to emphasize the physical idea that I'll shrink down the x-axis, I'll shrink down the y-axis in a way that I get one master curve. It's a beautiful idea. The idea is simple that where I can see it's going again and again inside, and I'm stretching out the concentration profile, but it can have again there's some sort of a similar geometric similarity in these shapes. Can I shrink them down or change them or increase, amplify them in a way that I just get one curve? And that's the entire idea of similarity. Okay? So I have to shrink down my x-axis and my y-axis in a way that I always get one curve. Okay? So that's the idea. So the idea is I'll define something, a variable, a similarity variable eta, which will be x by delta of C. Okay. And theta would be Ca by Cn naught in this case, but it may not be Cn naught, as you will see in your homework problem. This is something which is the amplitude, and this is the distance at which the concentration gradient is changing, and you get sort of one master curve. Master curve. And this is your similarity solution. Okay. So I want to again emphasize the idea is if you see some sort of similarity in shapes, what you're trying to do is you're trying to stretch out your x-axis at each time. Notice delta C is a function of time such that my master curve looks similar. Right? And that's what, when you think of it, this is what was when I was showing you this images of atomic explosion, right? They look similar. So why don't we change them in time in a way that they kind of collapse on each other? And that can give you all the information. Right? If you have something draining, a film draining, the film drains changes with time, but what if I just rescale in a way that I can get one snapshot and tell me everything? That's beautiful. This one line is just going to tell you everything about the solution. That's the idea of similarity. Right? So is to kind of find and rescale your axes in a way that you can get the solution. Okay. So this is a proposition. This is not to say this will always work. This is a proposition. And so what you're trying to do is convert TDE into an ODE. Okay. So I have so many curves. Okay. So I have so many curves of CA going with X at different times, but I want to convert from C of X comma T to K of theta of theta so that I just get one curve. So this is the idea, TDE to ODE. So CA of X comma T goes to theta of theta. That's the idea. Okay. Any questions on the idea? Does it make sense? Yes. Absolutely. Kind of collapsing them on this one curve. And by the way, you see this a lot in your research problems. Master curve, right? It doesn't have to be similarity always. You will be doing different kinds of experiments, modeling, and you will be trying to make sense through one plot, right? Sometimes one plot defines your PhD thesis. It happened for me. The one plot trying to kind of explain what is really going on, the physics of the problem or a trend. And that's the idea that the whole system can be summarized in one sort of trend. Okay. So that's very important. So this is the idea of similarity. So let's try to make more progress here. So how do I even come up with this number? So I have this del CA by del T is equal to dA del square CA by del X square. Okay, so this is my region, and this is sorry, not it's infinite. So this is what I have. And so how do I go about this? The idea is this: we know delta CA, so use order of magnitude analysis. And so the idea is this: delta CA is CA naught minus 0. We know that. I mean, that makes sense, right? That is going to be the change always. T. So remember that del CA by del T. I think I discussed this last class as well. But just to emphasize, don't forget this, that is how we will use the order of magnitude analysis. Is define the derivatives as delta CA by delta time, and delta time is simply T, because time difference is always going to be time, and space difference. The second derivative is delta CA by delta X square. So time is time, and delta X. So what should I, let me just, don't forget this similar symbol. And what is delta X? Any idea? What will be the delta X across which I'm seeing the concentration difference? Boundary layer, right? That has to be boundary layer, because that's my definition. What is the length scale? It's infinite or the boundary layer. Right? There is only two lengths, and it has to be boundary layer, because I'm only interested in the region where I have delta C naught, change in concentration. So delta C naught, or sorry, delta C. So I get CA naught by T is similar to dA CA naught by delta C square, or this goes to delta C is square root of dAT. Okay, so this proposition then becomes my eta should be X by delta, or X by, I propose it to be like this. I'm saying that, and this makes sense. As I'm going with time, I'm going further and further. I'm shrinking down my x-axis such that I'm getting a master curve. So look at this, is very important. So physically, to appreciate this, just to show you this, that we have these curves. We are saying that the delta C is stretching square root of time, larger and larger. And I'm shrinking down my x-axis to square root of time so that I get one master curve. That's the idea. All right, let's go ahead. Any questions on this idea? Yes. Right. Right. I mean, yes, that's correct. I would say mostly that's correct. It doesn't have to be that way. So you can choose to have some other, like a dimensional scale as well. But I would say just as good practice, it should be dimensions. Makes sense. Any other questions? All right. Okay. So let's just do some. Remember that I will not finish the entire problem, but I'll quickly give you the last few minutes just how to go about this. So remember, our theta is CA by CA naught. Okay. And so I first, and my left hand side is del CA by del T. Okay. So I will write this as del CA by del theta times del theta by del eta, or rather d theta by d eta, because theta is only a function of eta, del eta by del t. This product rule. Whenever you see something like this, remember that you want to go from first, you want to differentiate by your y-axis and your d theta by d theta and d theta by d. And you can see I'm just very guessing it. So product rule. This value is because I know the value of CA. This is CA naught. Okay. And my eta is given here. And this is a trick I would say all of you should remember. When I was, a PhD student, I used to always, hate these derivatives. But we can be more intelligent about it by seeing that eta has a 1 by square root of time, right? Eta has a 1 by square root of time. And when I'm differentiating with respect to time, I know I have 1 by square root of time and I will decrease the power like minus 1 the derivative. It become a t raised to power 3 by 2, the denominator. So what I'm saying is this is essentially you can write this as minus eta by 2t. Okay. Because what you're saying is you are just decreasing the power by t in the denominator, right? And a minus half comes because of the coefficient. So you can do more formally. You can say del eta by del t is minus x by 2 dat. This is the way you would normally do this. But I'm saying you can directly write this if you just sort of practice a little bit. It makes your life much easier. It makes your life much easier. So if you do this trick, so this becomes CA naught d theta by d eta into minus eta by 2t. Okay. So we are just running out of time. I'll give you the final two values of how to go about this. So del CA by del x is del CA by del theta d theta by d eta and del eta by del x. This is simple. This comes out to be d theta by d eta 1 by square root of dat. This is 1 by square root of dat. Then del by del x of dCA by dx is actually equal to del square CA by del x square, which is equal to del by del eta of CA naught d theta by d eta square root of dat times del eta by del x. And this comes out to be CA naught square theta by d eta square by dat. Okay, so these are the two terms. We get this one here and this one here. Okay. So this is product rule. What I'm first doing is taking the derivative with respect to x. Again, product rule. Del eta by del x can be found from the formula for eta, right? Eta should be here. X by square root of dat. So if I differentiate with the x, I get 1 by square root of dat. And then I take another derivative with respect to because I have a let's see what x in the equation. Del by c by del x is del by del x of del c by del x. Del c by del x is actually known in this step here. This one here. So push this here, right? I'm substituting this value here. And then I'm again taking a product to del by del eta. In the next class on Wednesday, what we will do is we'll substitute this and find a self-similar solution. From there, we'll go further and start to see more methods that kind of give you. And again, in a homework problem, you will do a similar problem with a boundary condition change, just to kind of show you how things become a little different. Is that in that case here, our y-axis was simply CA naught. We knew y-axis always starts with CA naught, right? In that case, your y-axis will also increase. So you'll rescale both y-axis and x-axis. And that's just it's a step up from this problem which you do in the class. And of course, we have another video which will show you. But the idea in self-similarity is always rescale your x-axis and y-axis to get 1 mark. All right, so we'll start talk more on Wednesday. And I have office hours in case you have any questions. I'm happy to take until the next 1 hour or so. So let me know if you have any questions.